Today we are doing something else. I have this Spindle Servo motor, can go up to 6000 RPM, 7.5 kilowatts, 3-phase, 380 volts. It's quite big, it's 21 inches. And the plan for this is to power this CNC lathe spindle, 8 to 5 here. But the motor, being 21 inches, will end up somewhere here. So I cannot put it on the side. And I don't want to put it on the back because, I don't have too much space here. It will be too long. So I'm planning to put it under the spindle and somehow cover, where the bed comes, cover the motor, seal it properly so coolant is not going there. Anyway, so I need to power this and see how it works. And I have the drive here. They claim 39 amps. I don't think so. It's 39 amps here somewhere. Right, so that's not true. Probably it's 13 amps because you rate that per phase. So 13 amps makes more sense. The problem is it's 380 volts and I don't have that here in the residential area. But I do have 240 volts coming here. Right, I have a 40 amps filter and 240 volts coming here. And I have this monstrosity. This is a converter from 240 volts AC. So I have ground wire and the two hot wires, 240 volts, and converts into 380 volts. So the output here, we have the neutral and the three phases, 380 volts between each of these two. And there was no ground for some reason. I had to wire a ground up here and this nut on the chassis. The way it works, the way they build this, they put a regular VFD. This is a 14 kilowatt VFD, can go to 500 hertz, so I can power a motor here, right? Quite powerful. And they run through some chokes and this transformer, but it's not wired as a transformer. It's not wired as an auto transformer and not as an isolation transformer. It's actually wired like some sort of a filter. So the outputs, these three wires are the three phases, UVW. Each one of them goes into one of these chokes, then goes into the coil, and it also comes out at the exit here through this switch. So I did a schematic of that. This is how it is. This is an inverter, the three chokes, and there is a star connection here on that transformer, which is not a transformer. All the inputs UVW go directly to the output. This is a neutral, artificially created, and there is also three capacitors connected here and connected together and nowhere else, not to the ground, nowhere else, right? So this gives you 380 volts here, and from neutral to any of these three you get 220 volts. So this inverter is not a pure sine wave inverter. It's more of a trapezoidal chopped PWM inverter. So I want to see how good that wave is, and is it exceeding, the maximum voltage which that drive requires, because I don't want to burn this and I don't want to burn the motor. So I put the oscilloscope here. I have a high voltage probe here, which is galvanically isolated because you cannot measure high voltage with the oscilloscope because of the ground. And we're gonna look at the sine wave, and then this is powered by a USB USB pack, right? It's powered with this wire. Gonna look at the waveforms and do a signal analysis to see what noise we have there. So I'm gonna wire this up and we take a look. Okay, so I have this wired here between two phases. The high voltage probe is disconnected for now. I'm gonna power this up. So this is the mains coming into the inverter. It shows 244 volts there. And to start it, actually there is a panel here at the back. I just have to press this green button and it's doing a slow start. That's the frequency. So they are running a VF curve, and you'll see the voltage going up here. Will stabilize against 400 there. So now it's ready to power. So switch that on, and let's see what we see, right? Like what this guy is gonna show. AC, put the wire into right, 389, 387, 390, okay, 385, and then here to neutral 220 something. So okay, let's see what this guy is saying. Auto. So what do we have here? I have a 391 volts RMS. It's more than 380. But what bothers me, there is some noise here. You can see the noise from the switching. What bothers me is this max voltage, 584. Because usually when you have a 380 volts, multiply with the square root of 2, it should not be more than 537 volts. But I get max there is 584. So 584 by 537, that's 8% more, right? So the peak to peak, you see there, 1.17 kilovolts. And RMS here is 390. 390 by 380. It should be okay. It's only 2.6%, but that extra voltage there bothers me because the IGBTs in the drive will burn from the high voltage. So I have the option. So this inverter, it's running a VF curve, so that's voltage frequency, right? As the frequency increases to the nominal frequency, which you can see here, 49 point something, that's the nominal frequency, the voltage increases as well. So when you get to 50 hertz, you have the programmed voltage. That 49, 50, I can adjust it from here, right? I can turn this knob and change the frequency, but if I go higher, the voltage goes higher. If I go lower, which I would like, lower voltage, then the frequency is not 50 hertz. So what I think I'm gonna do, I'm gonna find a manual for this and adjust that VF curve, because I can set it up so I reach 50 hertz when I have exactly 380 volts, or maybe I go even lower, 5-10%, so that peak is not getting to 584. So now let's look at to see what noise we have there. Where is it? So we go here, turn off the measurement, and we are in the FFT. Again, let's do an auto on FFT, and let's do exclusive here. Okay, and then let's make it set up itself, and then we'll go at a higher, more points, so we have more granularity there. Okay, that's how it looks like. So probably this is the fundamental, the 50 hertz output, and there is some spike here, right? Let's see what Henning 200 hertz. I don't know, should I center it at a lower frequency? Center at 100. Oh, I see it better. Okay, let's try with that. And then 1 kilohertz per division. We see better if we change that. That's the minimum. Okay, 2 kilohertz. Okay, so what you see here, because it's 2 kilohertz, you have 2, 4, 6. That there is the carrier frequency for the inverter. It's running at 6 kilohertz PWM frequency, and it's not at 0, you know, there is a component there, right? Because this would be 0 otherwise. So, and then I also have an artifact here, a little bit over 50 hertz, but it's not looking that bad. I mean, if I go back to the wave, maybe we can zoom in into one of them. Let's do a zoom here, maybe move it to the right. Yeah, so that there, it's this zoom here. See, you can't see much there. Maybe if I yeah, so let's capture one wave. Okay, that's the switching there. I put the cursor, one here at the peak and one here. That's 6 kilohertz. So overall it doesn't look that bad. I was expecting worse than that with a lot of noise. Here is a third frequency, right? So you have the 60 hertz and you have the 6 kilohertz here chopping, and there is one here like an artifact here at a different frequency, right? So this undulation here is from here to here, right? Whatever that frequency is, it's less than 50 kilohertz but greater than. So I don't think that counts too much, because the input in the drive there is a bridge rectifier followed by a capacitor bank. I think I'm gonna also try to. I have this line reactor, 30 amps. I measured it has 360 microhenry for each of these. I think I'm gonna put this to see if there is any improvement there. That 40 voltage swing I have there at the top, I measure with the cursors, it should drop to about 25 if I put this. So these two actions I'm gonna take. Change the VF frequency in the drive, so when I get 50 hertz I have about 370 volts, and the reason for that is 370 plus those 40 volts, you know, I'm getting 410. Maybe I go even lower than that. And then put this reactor to see if I can eliminate that chopping there, and then I'm gonna try to power the motor. Okay, so I put this oscilloscope I have, which is newer and has more points here. You see 10 million points per second, I think it is. And I zoomed in on the wave, and then I use the cursors, the vertical cursor. It's across 10 peaks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you look here on a delta x, it's 1 delta x 1.688 milliseconds. We divide that by 10 because we have 10 peaks, and so 1 divided by 0.000168 gives us, that's the frequency, so that's close to 6 kilohertz. That's the carrier frequency. And then the other cursors, the horizontal ones, they measure that peak to peak there, that oscillation there, and then we can see that here it's about 26 volts, so it's not 40. And I'm at the peak of the wave. I'm gonna zoom out, right? So that's that. So let's run it in auto. Take the cursors out and move this. Maybe see a couple waves. I'm getting the same RMS 390 volts here, and 580 the peak voltage as with the other oscilloscope I used. So this doesn't have a FFT of signal analyzer, so I cannot see the frequencies, these three frequencies, right? One, the chopping, and this one here, and there are more than that. I'm not gonna see that with this oscilloscope, but this is better because I can look at that wave much better and see what's there. So I'm gonna look for the manual and do some adjustments here and we come back and look. I was able to find the manual for this, and I took some of the parameters out of the VFD through this control panel. You just go over the parameter and see what the values are. And I took only the one relevant for what I need here. So this is voltage frequency control. It's operated from the control panel, meaning this control panel. And it has this frequency, preset frequency. That's the frequency you would run when you started, and you adjust this here, right? And then it has also the max frequency you would be able to set it, and frequency upper limit was at 50 Hertz. These two I changed from 55 to 50 Hertz. And the carrier frequency was 6 kilohertz like we saw on oscilloscope. I changed that to 8 kilohertz. And here's an explanation they provide based on the carrier frequency. I don't have a motor here, I'm driving the Spindle Servo driver, but what we see here, noise, right? The noise in the motor, or what follows the inverter, it's small at high frequency, but the drive temperature will rise at high frequency because of the IGBT transistor switching, and there is interference radiation created on the line back to the mains, right, back to 240 volts. So we're gonna look at that. So what I did here, these were the motor setting like you would power a motor: 11 kilowatt, 370 volts, 25 amps, 50 hertz. I changed this to 360. I made it smaller, right? So that's changed to 360 volts. Goddamn pen. 60 volts. Okay, so let's look what we have now. So you see the voltage is lower now, right? And it's the waveform now. I mean, looks better. I don't have that. Let me get a pen. With this carrier frequency changed to 8 kilohertz, I don't have the ripple here, that ondulation. I have it here now. But anyway, here's what my multimeter shows me. So I'm gonna put that into, see if I can do it without electrocuting myself. Right, so it's not 360 what I said, it's a little bit higher, 370, and it's similar for the other one. And this guy reports here RMS 385 volts. So yeah, that's close to 380 what I need. But the peaks are no longer 580 volts, right? It's 540 something. If you look here at the average is 546. So I dropped that peak at 580 volts. And that's average, right, over 1,000 waves. And then similarly the V minimum, where is that? This guy is 565, right, from 580. So it's much better. Now what I don't know is do I just start this up in the state it is now and just put that directly there in the drive, or do I need to have it connected and start this from the control panel so the voltage slowly grows to provide power to the drive? Because the drive has the capacitors, right? And the capacitors, when they're discharged, they're like a short circuit. So putting 360 volts into a dead short will drive a high current in this. It has protection, but I don't know. On the other side, what I'm thinking, maybe this has a soft start. So usually when you charge a high capacitor bank, you have a series resistor, power resistor, and the voltage goes through that resistor to charge the capacitor, and when you reach a threshold you shunt that resistor with a relay so it goes directly. So if that's there, then I don't have this surge problem. I'm thinking, before putting power on this guy, I have a 5.5 kilowatt motor here. I have this 5.5 kilowatt motor. This I'm using it as sort of a filter, if you wish, because this is my three-phase 220 volts power, again from 240 volts AC. Again, I'm using an inverter, powers that motor, but that motor has no load, and then I take power from here, three-phase 220, through a line reactor, and I power my surface grinder. Has a three-phase motor, 220 volts. So I'm thinking to actually power this motor. I mean, I can disconnect it from here. Now it's isolated. I can power it, all by itself, and I can use. Let me see. I can use this guy. Use this guy. Put it here. Well, I need to change this to that, but I have them somewhere here. And connect these wires, like three-phase, 3 wires and ground, to this guy, and try with the voltage up. Just try to power from here, and that will tell me if there is a protection in this guy, and it will stop the high current, because that has no soft start. We're just gonna try to start directly. It's quite big, has big rotor inertia, but 5.5 kilowatts. So that's what I'm thinking to do before even powering this guy. So yeah, I'll see what I can hook up, and then we'll come back here. So I have this powered off. You see, 0 voltage here, and I have the probe on the 240 volts main, and we are looking at that wave. That's how it looks like. And I'm gonna power this converter to see if we can see any switching noise showing up on that wave. So here we go. We are at 200 volts, 300, 360. So I'm not seeing anything. So maybe 8 kilohertz is fine. Also, I mentioned I'll use this motor, but it's wired for 220, so I have to take it out from there and reconnect the terminal for 415 or whatever. I think it's 400 volts to do that. So yeah, I think this will work. I need to find in the parameters where you control the max current. I mean, there is a current here you set for your motor, but that's just the RMS, the average. You need to find where you set the peak current, which will protect this drive. It's lots of parameters. This VFD, it's way much more complex than the El Cheapo here. That's a 7.5 kilowatt, right? It's not only the power, just look at the size of it. It's also, to this terminal, you can have an encoder coming from the motor. It's way more sophisticated than the other one. So let's see. I opened the drive to see if it has protection inside. So these 3 blues are varistors. They protect for voltage spikes. And those 2 greens are, I think they are NTCs, negative temperature coefficient. And those are to limit the current. This is the spec for the varistors, S14K625, 1650 volts and 50 amps for 625 RMS or 825 DC, and it can withstand 4500 amps for 20 microseconds. So this will take all the voltage spikes from switching or whatever, right? So that's gonna protect on the voltage mode. This is gonna protect on the current mode. I could not find online any data sheet for this. But supposedly this is the cold resistance, 30 ohms. So you put 380 volts through 30 ohms, you get 10 amps. The capacitor charges at 10 amps. This heats up, the resistance drops to 0 or very low, and then you get full current there. And as a DC bus, it's made of 6 capacitors, 820 microfarad at 400 volts. Maybe you can see there. But I'm not sure if that black thing there is a relay with a resistor or just protecting for current with these tiny NTC limiters. So what I think I'm gonna do, I have this this is an auto transformer, 5 kilowatts. It was from 120 volts to 240, but I modified it and I extended the secondary, well, if you wish, and now I can do multiple combination. If I put 120 here on these two terminals, or I mean they're connected vertically, then from here to here I'm getting 240, and from here to here I'm getting 380. So just connect, or if I connect 240 here, then I'm getting from here to here 380. So I think I'm gonna connect my 240 volts here, get 380 out, just one single phase. Connect that single phase here on between R and T terminals, and if I hear a clicking noise, that's the relay, the pre-charge relay, to protect the circuit. If I don't hear that, then it's only this inrush current limiters in the way. So we'll see what that gives us. Okay, so I have this wired power comes in here. The two hot wires, it's disconnected now, enters this connector block and then goes here as I mentioned. So one here on this bus and one here, 240 volts, and then from here to here I'm getting 380. So one wire goes to the inverter and the other wire, so these two go into the R and T. So I'm gonna leave this here on the driver. Maybe you can hear that clicking when I'm powering it up. Do you hear that? There's a clicking there, so I think it's fine, it has protection. That error 9 is because the encoder is not connected here, and it's complaining about that. But I think that should be fine. I have all the protection I need in the servo drive. Voltage, current, slow current on startup, slow startup. This doesn't have too many harmonics. I'm controlling the voltage, the peak voltage. So I think it should be good to power everything. That's the braking resistor for the servo drive. So when you have a spinning chuck, at that chuck is the chuck spinning at 2000 RPM and you stop the spindle, all that energy has to go somewhere. So it goes into this. It's a 2 kilowatt 30 ohm resistors. So I think I'm gonna hook it up and all the wires, the encoder wire, the power to the motor, and start jogging this motor, and then we look at all the other parameters. It's all wired up, the motor, servo motor, Spindle Servo drive. I have the manual here for it. This is powered, but nothing on the output here. I'm gonna turn it on. Nothing blew up. Shows me zero rotation there. If I spin on the shaft here, it shows me based on the encoder the direction is moving. So I need to enable one thing I observed, these suckers wire the terminal on the motor wrong. I had this wire correctly wired here. You see UVW, that's how they were, UVW, and this was spinning like crazy. And I flipped U and V, and now it's working correctly. So it came from the factory. The wires here are wrongly connected. Anyway, let's go enable the drive. So that's parameter 98, P098, enable. And now this is locked. You cannot turn it. It's because it's under control, right? It's fighting my position there. And by the way, this can go in speed mode and position mode, so that's why I want to use it, because I can use it as a C-axis. So more later on that. So now that's that, and then we're gonna do a jogging. So I had a jog speed set at 3000 RPM. Where is it? Here. Function, jog. If I press this, speed is gonna go up, and I think I set the maximum speed 3000 for the jogging operation alone. So here we go. Oh, it reset. Okay, 100. Yeah, because I didn't save it. So let me change that to go to parameter 76. Let's do this 3000 RPM. I wish there was a better option to set this up than this stupid thing. Okay, that's okay. 3000 and something. Go back to jogging. It's vibrating because it's touching here, right? But it goes in one direction, and if I press the other one, it goes in the opposite direction. So that works. Let's do a slower speed. Where is it? P76. Let's go 2000 RPM. Let's call that 2000. Pretty smooth. So I think it's in speed mode, and we should see that in the parameters here. Usually the beginning no, this is a reduced manual version. I have the full parameters with explanation, but it's in Chinese. This is 36 pages. The full version is 115 or so. So I don't think I have all of them here. I should be able to find that. How do you limit commission? No, spindle. No, that cannot be here. Usually there should have been a section for speed mode and a section for position mode. Yeah, I need to print that. I translated that Chinese manual using Google Translation. Took a while. I still have like 20-30 pages not yet translated. Maybe I can find that. Anyway, so let me tell you about the features of this, right? So you can control it in speed mode with the voltage, right, from 0 to 10 volts, and you map that to a speed like 0 to 6000 or 0 to 3000, whatever you like. And then if you want to run this as a z-axis, which it's the same axis with the z-axis, then you switch this into position mode. Now you're feeding it pulses and direction like a regular stepper motor or a servo motor. So then what you can do, you machine with the C-axis on the spindle, right? This guy rotates under control, like from the G-code on the C-axis. And if you have a live tool, like a end mill on this side or on the side of your part, you can machine that, right? You're gonna do more than just lathe operation. And in one of those 4 boxes there, I have a CNC controller with 5 axes. So that will give me X and Z, regular lathe stuff, Y, which is the turret moving up and down, right? And then one of these axes is used as C-axis, right? Because you control this speed and position. Now, for position, what I don't like, the encoder is only 10,000 quadrature pulses per revolution. So that's not a lot. If you want any precision positioning, you need a better encoder, right? And this is an incremental encoder, is not one of those digital encoder which have a serial protocol. You just have the A, B, and Z differential lines coming into the encoder, into the controller. But what I'm planning to do to get a better resolution and actually change that encoder with one which gives me 255,000 points per revolution. The problem with that is if you run this at 3000 RPM, so many pulses per revolution per second, this drive can handle. So I need to put something in between which reduces that pulse rate, by a well-known factor. Like this is called gearing, right? So the idea is, are you running in speed mode? Then I'm running with that pulse rate reduced by a factor of 8 or whatever this drive supports, right? I can trick the driver. I can send one of these ports here, RS422 commands, and I can configure that from software from a microchip, right? And then once I want to switch to a Z-axis to do machining, then I eliminate that gearing in the encoder. So now this guy is strict and is running at very low speed. You don't need high speed when you machine here, running a low speed with a high precision encoder. And I'll have to do that for the lathe, for the spindle, because one of these ports here is for a second encoder which stays on the spindle. So I'll have to do the same thing there. The problem there is that spindle has a large diameter on the back, so I need probably a very expensive encoder. You know, I have to mount an encoder here, so not obstructing the hole. So I'm gonna have to print that manual and come back here and we test the rest of the features. Also, when you switch to the position mode, there is a procedure here where you orient the spindle, so it goes to 0, or you tell it how many points to go from 0 in, you know, and you get that 0 position. When at that specific moment, when you zero the spindle, you switch between these two encoder modes from high resolution to low resolution. So yeah, I'll be back. I removed all that bracing which was rattling on the mounts, put some newspaper as a cushion. This is the jog speed, 5000 RPM, P76. P76 jog speed, default 100. I changed the acceleration from 200 millisecond per 1000 RPM to half a second. So to 5000 RPM, you're gonna need 2.5 seconds acceleration and deceleration. So I'm gonna jog it now with that configuration. Let's go to function jog. Here we go. 5000 RPM. So works. The only problem with that, I'm not gonna be able to machine anything at 5000 RPM. Who's spinning lathe spindle at 5000 RPM? Also, my plan was to have a 1:2 ratio between the motor and the spindle to have more torque for that Z-axis configuration. But this guy came with such a small diameter pulley here that I couldn't find the 1:2 ratio to mount. This is 38 millimeters, 1.75 inches. I couldn't find anything because the diameter is so big and there's not enough meat for the teeth. So, you know, I have to live with 1:1 ratio and live with that. That's okay, because, you know, this is a hobby here. Nothing, don't need super precision stuff. But I'm satisfied with how it works. This whole table is vibrating because it's not clamped, just sits here. So we'll do the functions next. I have the full manual printed and I'm preparing a configuration here to have all these control wires coming up in this breakout board, so I can connect them to, you know, 24 volts and 10 volts for the spindle control from 0 to 10 volts, where I can adjust the voltage here in 0.1 increments, you know. But I'm waiting for some switches, like temporary switches and regular switches, to turn on and off the spindle, trigger the spindle orientation, switch the motor from speed mode to positioning mode as a Z-axis. I'm gonna have to take all these functions one by one and evaluate them. And I thought, in the meanwhile, while I'm waiting for those parts to come, I could finish this box, because I don't like this thing here, and the panel they have here too. This looks like a temporary thing. So what I'm gonna do, I'm gonna come up with a wire. I'm gonna make a hole there, put one of these things, a gland, with the wire through that, and directly connect it inside the box in the terminals there. And then for the output, I'm thinking to have 2 sockets, and I found the best position. It's here on top. Here I might have some space, but kind of crowded. Don't want to do that. And also in the back, not enough room there because I have a fan. So I think it's the best option for me. Also, there is an advantage. I can take the handle off, take this cover off, put that on my milling machine, which is exactly what I'm gonna do, and drill these holes, then chew them up with an end mill, and then use a boring bar to make that hole here. And I'll sandwich this between two pieces of aluminum, maybe 1/4 inch thick, so I can bore them out. So, you know, if I align here on the mill, I can do this and then move to the other one. I have them both knocked out. And this is the connector I'm using as 3-phase with these are the 3 phases, and that's the ground. And last time we tested this motor, played around with it, but I forgot to power the fan, which is not coming from the motor. It needs to come directly from 380 volts because that fan is running all the time. So that's what I'm gonna do now. Okay, so we have this all worked out. I have the 2 3-phase connectors here. This is for the fan, which I wired there with the yellow wire. I'm gonna run without fan because it's noisy, just so you see how noisy it is. You can hear it. It sucks air from here and blows to here. So I'm gonna run without the fan. I have here my analog voltage source. It's set at 4 volts. And I have this testing fixture where I have 4 power supply, 5 volt, 12 volt, and 2 24s. I'm using the 5 volt for this MPG, which I'm using as a source for pulse and direction when we are running in the positioning mode. And I'm using one of the 24 volts to drive this optocoupler board. And what I have here, I have the feedback signals, and then I have this panel. These 2 rows are latching switches, these 2 rows are momentary switches. So if you look at the feedback, I have the ready LED, which means the servo spindle is ready, and that's the alarm. I have no alarm. It's at 0 speed. That ZSP means we are at 0 speed. ASP, which is the next one, means we are at speed, at program speed. Whatever that program speed is, either we are running in voltage mode, speed mode, or positioning mode. And then the OC is for orientation complete. This button here will trigger the spindle orientation. And then the next one here is for switching in positioning mode. So that C-axis switch, you activate it from here and it feedbacks there. So we're gonna test the servo on. Is just putting power and keeping the motor in position. So we're gonna turn this on, and now you cannot turn this because it's locked. And then we turn this off. You can run all this without the spindle being on. So I'm gonna run the forward motion. If I latch it, just runs 4 volts. It's 2400 RPM. Can increase the voltage here, going up. 3700 RPM. I'm gonna keep it low for now, maybe at 4 volts or something. So that's forward. And then we have the reverse. That's running fine. And then we have the spindle orientation. As you see, I keep this pressed and comes back in the same position. You can change where it should be located, and this is useful for if you have a milling machine and you need to orient the spindle to grab the tool from the socket, from the tool changer in that specific position, because you have the dogs on the BT40 tapper or what have you. That's where you adjust the parameter to finish the orientation in a position you want. And you have 10,000 steps per revolution, so you can adjust it very accurately. And then finally I have the switching to positioning mode, where you can send pulses. So when you do that, you get the confirmation there that these are not working anymore. Okay, and then I don't have a signal, direction and pulse generators to test this, but I wire this encoder and I change the parameters to accept quadrature signals. So if I spin this, I'm running a a gearing mode where I'm amplifying, you know, a tick here translates with 400 ticks there. Otherwise, this has 100 ticks per rotation, and if I turn one turn, it's just 100th of a rotation. You're not gonna see anything there because I will have to spin this 100 times to get one full rotation. So with that gearing, I can do that very easily. One thing I want to show you, when we spin, the ZSP zero speed goes off, obviously, because we are not zero speed, and also that at speed, it's gonna turn on. Now the program speed is 0, right? 0 speed, and it's at speed, which is 0. But if I run any forward or reverse, the 0 speed will turn off. That at speed will turn off momentarily until it reaches the speed, and then it stays on. So let's see that. See, it's at speed. And again, at speed 0 and 0 speed. Same here. So, seems all works fine with this guy. And I can use it for that CNC lathe spindle. That will be way much later because I need to make a design for that. And I didn't make up my mind. So, that's it for now.